Chemistry is often called the central science. It's a vast and intricate field. At its heart lies the concept of chemical bonds. These bonds are the glue that holds atoms together, forming molecules. Understanding how and why these bonds form is crucial to unlocking the secrets of the molecular world. Delving into the fascinating world of bond energy, a fundamental concept in chemistry. To explore the forces that govern bond formation, the energy changes associated with breaking and forming bonds, and the implications of these concepts in various chemical reactions. Welcome, science fans, on this journey as we unravel the mysteries of bond energy and appreciate its significance in understanding the behavior of matter at the molecular level. Before we can understand bond energy, we need to grasp the fundamental forces at play within an atom. At the heart of this dance are electrostatic interactions, governed by Coulomb's law. Coulomb's law describes the force between two charged objects. In the case of bond energy, two charged particles. It states that the electric force F between two-point charges is directly proportional to the product of the magnitudes of the charges Q1 and Q2, and inversely proportional to the square of the distance r squared between them. The law can be mathematically expressed as opposite charges attract, just like the poles of a magnet. This attraction holds the atom together. Now, let's delve into the heart of the matter: bond energy. In essence, bond energy is the measure of the strength of a chemical bond. It quantifies the amount of energy required to break a particular bond between two atoms in a gaseous state. Imagine two atoms held together by a bond. To separate them, we need to overcome the attractive forces holding them together. This requires energy. The stronger the bond, the more energy is needed to break it. Bond energy is typically expressed in units of kilojoules per mole. This represents the energy required to break 1 mole of bonds in a substance. It's crucial to understand that bond energy is always a positive value. This makes intuitive sense because breaking a bond always requires an input of energy. The concept of bond energy is central to understanding chemical reactions. It allows us to predict the energy changes associated with chemical transformations. As we've established, breaking a chemical bond always requires an input of energy. Think of it like trying to separate two magnets stuck together. You need to exert force and therefore energy to pull them apart. This energy input is needed to overcome the attractive forces between the positively charged nuclei of the atoms and the negatively charged electrons they share in the bond. When we supply enough energy, we can overcome these attractive forces, causing the bond to break. The energy required to break a bond is called the bond dissociation energy. This value is always positive, reflecting the fact that bond breaking is an endothermic process. An endothermic process is one that absorbs energy from its surroundings. In a chemical reaction, bond breaking is often represented by an uphill arrow in an energy diagram. This signifies that the energy of the system increases as bonds are broken. Forming bonds: energy release upon formation. Just as breaking bonds requires energy, forming bonds releases energy. This is an exothermic process, meaning it releases energy into the surroundings. Think of it like allowing two magnets to snap together. They release energy in the form of sound and heat as they come together. Similarly, when two atoms form a bond, they release energy, typically in the form of heat. This energy release occurs because the system is moving to a lower, more stable energy state. Atoms are inherently more stable when they are bonded together than when they exist as isolated entities. In a chemical reaction, bond formation is depicted by a downhill arrow in an energy diagram. This signifies that the energy of the system decreases as bonds are formed, and energy is released into the surroundings. Enthalpy change, a reaction's heat signature. Now that we understand the energy changes associated with bond breaking and bond formation, let's explore how these concepts relate to the overall energy change of a chemical reaction. This overall energy change is known as enthalpy change, denoted by the symbol dH. Enthalpy change is a measure of the heat absorbed or released during a chemical reaction at constant pressure. It tells us whether a reaction is endothermic, which absorbs heat, or exothermic, which releases heat. A positive dH indicates an endothermic reaction, where the products have higher energy than the reactants. Conversely, a negative dH signifies an exothermic reaction, where the products have lower energy than the reactants. The enthalpy change of a reaction can be calculated using bond energies. By considering the energy required to break bonds in the reactants and the energy released upon forming bonds in the products, we can determine the overall energy change of the reaction. Enjoying the video so far? Make sure to subscribe and hit the notification bell so you ace that chemistry class. Enjoy the rest of the video. Calculating enthalpy change bond energies in action. Let's calculate the DH for the combustion of methane, CH4. The reaction is CH4 plus 2O2 yields CO2 plus 2H2O. The standard enthalpy of formation for each species involved in the reaction is needed. The values, in kJ-mol, are approximately as shown. Identify the bonds broken in the reactants and formed in the products. Use bond energy values to calculate energy changes. Use the Hess's law formula. The enthalpy change for the reaction can be calculated using the formula. DH equals energy required to break bonds minus energy released forming bonds. The enthalpy change, DH, for the combustion of methane, CH4, is approximately minus 890.3 kJ-mol. This negative value indicates that the reaction is exothermic, releasing energy in the form of heat. This reaction is exothermic, releasing heat because it's negative. Bond energy and reaction spontaneity, a predictive tool. Bond energies provide valuable insights into the spontaneity of chemical reactions. A spontaneous reaction is one that occurs without the need for continuous external energy input. While bond energies alone cannot definitively determine spontaneity, they offer valuable clues. Generally, reactions that release a significant amount of energy, meaning they have a large negative delta H, tend to be spontaneous. This makes intuitive sense. If a reaction releases a lot of energy into the surroundings, it's more likely to occur spontaneously. Conversely, reactions that require a large input of energy, meaning they have a large positive delta H, are less likely to be spontaneous. However, it's crucial to remember that enthalpy change is only one piece of the puzzle when it comes to spontaneity. Entropy change, a measure of disorder, also plays a crucial role. Factors affecting bond energy, beyond the basics. While we focused on the fundamental concepts of bond energy, it's important to note that several factors can influence the strength of a bond. These factors can lead to variations in bond energies, even for seemingly similar bonds. One crucial factor is bond length, which is the distance between the nuclei of two bonded atoms. Generally, shorter bonds tend to be stronger than longer bonds. Shorter bonds make it harder to pull apart the bond. This is because the attractive forces between the nuclei and shared electrons are stronger at shorter distances. Another important factor is bond order, which refers to the number of electron pairs shared between two atoms. Single bonds involving the sharing of one electron pair are generally weaker than double bonds, which involve two shared electron pairs. Triple bonds with three shared pairs are even stronger. Electronegativity, a measure of an atom's ability to attract electrons towards itself, also plays a role. Bonds between atoms with similar electronegativities tend to be stronger than those with large differences in electronegativity. Bond energy in the real world. Applications and implications. The concept of bond energy extends far beyond the confines of a chemistry textbook. It has profound implications in various real-world applications, from understanding biological processes to developing new materials. In biological systems, bond energy plays a crucial role in enzyme catalysis. Enzymes are biological catalysts that speed up chemical reactions by lowering the activation energy. They achieve this by weakening the bonds in reactant molecules, making it easier for them to break and form new bonds to create products. In material science, bond energy is a key factor in determining the strength and stability of materials. Stronger bonds between atoms generally lead to materials with higher melting points, greater hardness, and greater resistance to deformation. For example, diamond, renowned for its exceptional hardness, owes its properties to the strong covalent bonds between carbon atoms. Understanding bond energy allows scientists to design and develop new materials with tailored properties for specific applications. Conclusion: the power of bond energy. In conclusion, bond energy is a fundamental concept in chemistry that provides a quantitative measure of the strength of chemical bonds. It allows us to understand the energy changes associated with breaking and forming bonds, which is crucial for comprehending chemical reactions. By considering bond energies, we can calculate the enthalpy change of a reaction, providing insights into whether a reaction releases or absorbs heat. This knowledge is invaluable in predicting the spontaneity of reactions and understanding the energy flow in chemical transformations. Moreover, bond energy has far-reaching implications in various fields, from biology to material science. By understanding the factors that influence bond strength, scientists can design and develop new materials with tailored properties and gain deeper insights into the intricate workings of biological systems. As we continue to explore the molecular world, our understanding of bond energy will undoubtedly lead to further discoveries and innovations, shaping the future of science and technology. Subscribe if you enjoyed this video. Be sure to have a nice night and good night.